Hello everyone, and welcome to PChem Recitation. My name is Ryan Zarni, and I will be the TA for this semester. I am currently a second year in the biochemistry program pursuing my PhD, and I am in Dr. Xing Ho's lab studying DNA and protein and how they have co-evolved together. My office hours are going to be on Tuesdays from 2 to 4 p.m. in MRB 250. Before we get started, I just wanted to go over what homework is going to look like for you all this semester, because there are some stuff that is very particular about this course. So first of all, homeworks are due before the start of your recitation section each week. So for the most part, I don't care as much which recitation section you go to, but you must turn in your homework before your assigned recitation section, or else I will not grade it. Secondly, you should expect to spend about 4 to 6 hours a week on homework. That's just a general idea of how much you should be spending, but overall on the actual homework, you should set aside at least that amount of time. For your homework, you must show all of your work, or else the problem will not count. So if you're going to program in MATLAB, Python, or Mathematica, you need to include a printout of your coding so that I can see that you actually did the work for it. And then for the overall grading of the homework, 50% of your homework grade will come from completion, and the other 50% will be randomly selected questions from that week that I will grade for correctness. And speaking of correctness, you must box your answers. If it is not boxed, it is not considered complete, and I will not guess where your answer is or what you thought was the correct answer, so you must box your answer ahead of time. Okay, so moving on to recitation for this week. We're going to be doing a mathematic review to go over some of the things that will help you succeed in PChem for this semester. So what we're going to be talking about in this lecture is calculus, specifically derivatives and integrals, and then we're going to talk about state functions as well as scientific notation of units and logs and some of the rules that you can use to help yourself with the equations that we're going to be using. So first of all, let's start off with a pretty generic function. So we have f of t is equal to t squared. So your standard equation, that's an exponential. We're going to look a little bit at this. So we want to get the rate of change over time, but how would we actually go about doing that? There's a couple different ways, and one of the most basic ways is to use the slope equation, which is a pretty simple thing. You guys probably did this all the way back to maybe junior high, but basically you take your rate is equal to your change in your function over your variable, which in this case is t, and then you take your final value minus your initial value divided by your final variable minus your initial variable. This is useful if you want to get an approximate of what you're looking at, but if you're trying to get a precise answer, you're not going to be able to do a whole lot with this. So that's really where the instantaneous rate of change comes from, which is also called a derivative. And remember that a derivative is a calculation of the slope of the line tangent to any given point on your function. So looking a little bit more into that, let's talk about what derivatives actually tell you. So the first derivative, as we said, is the slope of the tangent line to the function at any point that you have. The second derivative is the slope of the first derivative, so it's the slope of the slope, which can provide information on the concavity of your equation. So it can either be concave up or concave down, and that tells you the direction that your parabola is facing based on whether or not it's positive or negative. So breaking this down a little bit, let's go ahead and look at the generic equation for a derivative. So you have your change in f over your change in t, which is equal to your function times the derivative of your variable. So let's take an example of that where we have f of t is equal to t squared. So our first derivative, we're going to take that exponential that our variable has, so the 2, and subtract 1. So we're going to have 1 for our new derivative variable exponent, and then we're going to bring that value down in front of our variable to be our coefficient. So overall we get the delta f over delta t is equal to 2t. And then if we continue that on, we're going to subtract 1 again from the t value, and we get a t raised to the 0, which anything raised to the 0 power is going to be 1, so our t is going to go away, and we're just going to be left with our 2 value. And you can see down below we have different graphs for each of these equations. So our first one is an exponential, then we get a linear line, and then we get a single horizontal value for our second derivative. Okay, moving on, we're going to do a quick example of this. So we have y is equal to x to the third plus 15x. You can see the equation off to the right. It is an exponential curve, just as you would expect with x to the third. So when we take the first derivative of that, we're going to break it down into the individual parts. So we're going to take x to the third. We're going to subtract 1 from the 3 and bring that 3 down in front of our x. So we're going to get 3x raised to the second. And then for the second part, we're going to have 15x. So we subtract 1 from 1, get 0. Again, it's raised to the 0 power, so it's 1, and we're just left with 15. So overall, we get the first derivative is equal to 3x squared plus 15, which again, when you look to the right, is still an exponential, which we would expect from the x squared component. Then we're moving on to the second derivative. So the 15 doesn't matter anymore because we don't have an x, so it's going to fall off. But we're going to bring that 2 down and multiply it by the 3 and get 6x raised to the 1, which if you look to the right is a linear line, which is what we would expect. In addition to single variable derivations, we can also have multivariable derivations, which introduces us to partial derivatives. And what you're going to do is you're only going to touch what you are taking the derivative with respect to. So on the right, we have an example equation of f of xy is equal to x squared y plus 3x plus y squared. And we're going to take this derivative with respect to x and then with respect to y. So if we take it with respect to x, we're going to take the exponent for x, bring it down, and get 2xy plus 3. So in this case, we're going to treat y as if it is a coefficient. So it looks just like a number, which is why the y squared goes away, because we don't care about it anymore. And then if we take the full function with respect to y, we do the same thing but in reverse. So we get x squared plus 2y. Okay, so let's talk about integrals next, because they are extremely important. So integrals are the inverse of a derivative, or they're also known as an antiderivative. They're used to determine the area under the curve. They are so much easier than using a summation method, which you can see off to the right, which is where you have to draw different boxes to approximate the area under a curve. And as you can see, they're not extremely accurate because there are certain parts that are missing or overestimating the overall area. So overall, taking the integral is much more accurate. So we will take the variable that you're integrating with and raise the exponent plus 1 and divide by the coefficient of that new value. So basically, we're just doing the exact opposite of what we did with the derivatives. And then, in addition, we're going to have to add the constant c to indefinite integrals. As you saw earlier with the derivatives that we took, there was sometimes that the variable fell off, and we want to account for that in our indefinite integrals. With definite integrals, we don't have to worry about it because they cancel themselves out, and overall, that constant doesn't matter. But let's go ahead and look at a sample equation. So we have a first derivative equation down below with f prime of x is equal to 15x squared plus x dx. And what we're going to do is we're going to integrate with respect to x in an indefinite integral. And so when we do that, we get f of x is equal to 5x cubed plus 1/2 x squared plus c. So that plus c is extremely important because this is an indefinite integral, and we don't know what that value could be. So we would have to be given some sort of equation that we could solve it for, but right now we do not have that. And then when you do a definite integral, you go from one value to another. So it's written with a number below, number above, and then your integration equation. So in this case, we're going to be integrating from 0 to 5 with that same equation that we had up above. And so we're going to do our final minus our initial, and we're going to plug in our 5 into our equation, and then also our 0 into the equation. And after you do all the math with that, we get a total value of 650.5. Okay, so looking a little bit at the derivatives that we did earlier, we're going to talk a little bit about some of the applications that we can see with PChem. So with exact and inexact derivatives, exact derivatives, which we're going to call D, are properties of state functions. So they have a final and an initial form that are known, and the integral is equal to the final minus the initial value of the function. So an example of this is delta U, or energy. So it only matters what the final and initial part were. Inexact derivatives, we're going to call d hat in this case, are properties of non-state function. And so this is the case where the final minus the initial values for the function do not equal the integral for the function. So an example of this is Q, or heat. So speaking of that, what are state functions? That's a great question. So state functions are any function whose value only depends on the current state of the system, not how it got to that state. So I'm going to give you guys a quick example. A couple weeks ago, I went backpacking and started at about 9,000 feet and then went up all the way to the top of Comanche Peak over in Rocky Mountain National Park, which sits at 13,000 feet. So the distance is not a state function. It very much mattered that we had to go for 28 miles in order to finish our hiking experience, but the elevation didn't change based on the path that we took. Of course, it changed as we were going, but overall, the initial and final values didn't change at all. So we started at 9,000, finished at 13,000, so no matter what path we took, our final minus our initial is always going to be 4,000 feet. And then we're going to talk about scientific notation. I know that you all have been using this through all of your courses, but I just wanted to quickly go over it because sometimes it can get lost in all the equations that you're using for PChem, and it's important to keep track of all of your notation. So big ones to know is 10 to the minus 3 is going to be millimolar if we're using moles, for example. Minus 6 is going to be micromolar, minus 9 is nanomolar, minus 12 is picomolar. So a lot of this is going to come in when we do our kinetic section and we're talking about different KDs, which you guys will learn a lot more about later. And then another one is 10 to the third, which is, for example, here, a kilodalton. So make sure that you use scientific notation. It's going to help you so much and keep your page so much cleaner. And then we're going to talk about logs. So later on, logs will become a lot more important, but I wanted to remind you all of some rules that logs have that can make your life so much better. So just going with the general equation of log base b of x is equal to y. So remember that you can rearrange this equation to be b raised to the y is equal to x. So really that's what you're solving for. Another thing to remember is when you have a log of x divided by y, that's also equal to the log of x minus the log of y. So you can separate them out to make things a little bit easier, especially if you're using a more basic calculator. Next, if you have a log of x raised to the z, you can also rearrange this to be z times the log of x. Additionally, if you have the natural log of e raised to the x, that is just equal to x. So the ln and the e cancel each other out, which will be very important when we get to some of our equations in thermodynamics. The inverse of that is if you have e raised to the ln of x, again, the e and ln cancel each other out, and it just becomes x. So an example of this that you guys will see very soon is delta g is equal to the negative RT ln of k. And if we raise all of this to e to the power of this equation, we get e raised to the delta g is equal to e raised to the negative RT times e ln of k. And then the ln and e cancel out, so we get k is equal to e raised to the negative delta g over RT. So learning these log rules can make your life so much easier in PChem and make all of your homework and equations in class go so much faster. I hope this helps. If you guys have any additional questions, please feel free to stop by my office hours or bring those questions with you to recitation. I look forward to seeing you all.